So I want to welcome you tonight to this webinar with the Siskiyou Land Trust. We are a small local land trust in Siskiyou County, way up on the northern end of the state of California, and we do a variety of projects in Siskiyou County. We've got conservation easement projects with private landowners. The focus area for us right now on those types of projects is in the Scott Valley, where we hold conservation easements along the Scott River. And we're currently working on 4 projects that will place 40,000 acres, or a little bit more than 40,000 acres, under conservation easements, which place a permanent type of protection on those landscapes. And really the focus there is to keep them whole. So the conservation easements preclude future subdivision, and then also to keep those landscapes working. And it's been really great this spring to have these webinars tonight with Bill and last month with Michael Kaufman to talk about what we're seeing out in that area of the Klamath Mountains, and tonight the geology, but with Michael Kaufman, the conifers, to give some context for that area. That's home to the Russian and Marble Mountain Wilderness. And hopefully you folks who are with us here tonight are getting out to enjoy those places. I was out at Little and Big Duck Lake last weekend, and I ran into some folks in the parking lot who said, oh yeah, we know about the Miracle Mile. And I just thought that that was great. The Miracle Mile being an area of amazing conifer diversity. Within the Miracle Mile, they have located 18 different types of conifer species, which is a big challenge because the last 2 are hard to get to. But if you're really interested in it, I'm sure you can do it. When we're out in the field on these conservation easements that we're working on now, when we get into those pockets of diversity, we're seeing, 12, 13, 14 conifer species in very small areas. So that's been really neat for us. The Land Trust also has a concentration area in Mount Shasta. In Mount Shasta, we hold open spaces for public use. So Sisson Meadow is the place that people really know, with the boardwalks where you can go to enjoy the outdoors right in the middle of town. And we've got some other projects here. We work with the Trail Association to hold right-of-ways and easements to help trails be developed in the area. So that's a little bit of an overview of what Siskiyou Land Trust does. And I have mentioned it a couple of times, but I want to make sure that you're all aware. We've got 2 webinars that we did previous to this. The one that I've mentioned with Michael Kaufman about conifer diversity. And then earlier, before that, we did one with Tom Landis with the Southern Oregon Monarch Advocates about monarch butterflies and way station planting. So if you're interested in either of those, if you didn't get to see them, the recordings are posted on the Siskiyou Land Trust website. Yes. I'm really excited to introduce Bill here. He has retired now from College of the Siskiyous, where he was the geology instructor. He came to the faculty in 1991. I think I took my first geology class from him probably in 93 or maybe 94. So I've got some connection with Bill, and I love that he is sharing with us his knowledge of the area and his just love and enthusiasm for it. So now I'm going to turn it over to Bill, and we can hear what he has to say about the geology of the Klamath Mountains. Thanks so much, Bill. It's all yours.
Thanks, Renee. So what I'd like to do this evening, I was telling Renee that this is kind of a very broad overview of the geology of the Klamath. In the past maybe 5 years or so, there's been a real increase of interest in the geology of the Klamath as far as people coming to the college, and prior to my retirement in 2018, a lot of the focus was on regional volcanic, looking at the Cascades, Southern Cascades. But seems like since I've been retired, there's been a lot of interest in the Klamath. And over the last couple of summers, I've hosted workshops for Siskiyou Field Institute, and I host a Chautauqua short courses. And so you guys know the Klamath Mountains, they're this rugged upland. And they're kind of confusing geographically because they include several named ranges, the Marbles, the Trinities, the Eddies, the Siskiyous, and they span the boundary between northwestern California and southwestern Oregon. But what really unifies those ranges is that the fundamental underlying geology is the same, that what you're seeing is a series of terrains, basically thickened pieces of the crust that didn't initially belong to North America. And over the last several 100 million years, the subduction of the ocean floor that separated those thickened pieces of crust, what we call terrains, that ocean floor sank under the leading edge of the continent. And then those terrains, being thick and buoyant, couldn't subduct. So instead, they've been sutured onto the western edge of North America. And there's a really simple geologic map on this page, and you guys can see the eastern Klamath terrain here in brown, the central metamorphic terrain in orange, and then these other terrains in light green and kind of a turquoise color, and then finally the young rocks of the Franciscan, which are the modern rocks that are being added to the western edge of North America, although they're not a terrain in quite the same sense that the others are. So what we want to do is just look a little bit at the geology of the Klamaths, both the processes that form them, and then very, very briefly a little bit about the diversity and what the implications of that diversity are for soils and biodiversity, and also for sort of modern day geologic processes that are operating in the mountains. Okay, so just a quick word of introduction. Everybody probably knows if you were to cut Earth open, there's a dense metallic core, and then there's a shell of silicate rock that surrounds that, what's called the mantle. And then the very outermost part of the Earth is the crust. And it's mostly basalt, like you see in Hawaii under the oceans, and it's broadly granite under the continents. And basically, that's a sort of a positional layering of the Earth. But more importantly, the outer part of the planet, both the crust and the very upper part of the mantle, they're cool and they're rigid. And that forms what we call the plates. So if you were to take the Earth's surface on this globe and unfold it, you would see that it's actually broken into a series of plates of rigid rock, the lithosphere. And then what's kind of amazing is those actually float in a somewhat softer region of the upper mantle, softer and a little bit denser, called the asthenosphere. So the plates are floating on this asthenosphere. Then as you go down into the Earth, you know it gets hotter, but because of the pressure, the rock actually becomes more rigid, not less. So once you go below the asthenosphere, the deep mantle sort of has the consistency of silly putty. But it's that upper soft asthenosphere that the plates are floating on that allows them to move side to side and up and down. And so these plates that cover the surface of the Earth, they're actually able to move about relative to one another. And most of the geologic activity on Earth in terms of earthquakes and volcanoes is not in the middle of plates, it's at their boundaries. And here in the Pacific Northwest, we live along one of those plate boundaries. So the lithosphere, it turns out there's three kind of things that can happen. In some areas, plates can separate apart. And when they do, hot mantle rock wells up, it undergoes partial melting, it makes new crust. And so we can actually make new lithosphere at what they call divergent boundaries, where the plates are splitting apart. Now, if that's happening, then somewhere else, since Earth's surface isn't getting any bigger, somewhere else plates have to come together. And there's a couple ways they can do that. But here in the Pacific Northwest, the most important one is that a dense slab of ocean lithosphere that's under the ocean, that can actually sink down and sink back into the Earth underneath an overriding plate. And that's what's been happening here in Western North America for the last several 100 million years. We call that process subduction. And then there's a third type of plate boundary, which of course everybody in California is familiar with. That's where two plates simply slide laterally past one another, and those are the shear boundaries or the transform boundaries, like the San Andreas. So here in the Pacific Northwest, the key thing is that oceanic plates, dense ocean lithosphere, has been sinking beneath the western edge of North America for several hundred million years, probably at least 250 million years. And the assembly of the klamaths, those various terrains that comprise the klamath, are a direct result of that process. Okay, so here's the sort of picture of this. So what happens is when ocean lithosphere is born at a ridge, a mid-ocean ridge, it's young and thin and buoyant, and it floats easily in that asthenosphere. But as it moves away from the ridge, it cools, and the mantle part of it, the lower part of it, actually gets thicker. So the whole plate gets denser. And once it's more than about 10 million years old, it's actually denser than the underlying asthenosphere. And so if it gets pushed down, its own weight will cause it to sink back into the planet's interior. And we call that process subduction. So normally, ocean lithosphere is born, it moves away from a ridge to a subduction zone, and then it sinks back into the Earth's interior. So the problem arises when part of that oceanic plate is thicker or less dense than it normally is. Then we're going to see that subduction process doesn't work properly. So a couple of things about subduction. The geology here of the Pacific Northwest, it's really one of subduction, not only the Klamaths, but also the young high cascade volcanoes. So a couple of things. First of all, when a plate subducts, when it sinks back into the Earth's interior, it sticks and slips. It doesn't subduct smoothly. And of course, when it sticks, a huge amount of stress is built up in the rocks. Eventually, they'll overcome the strength of the rocks will tear and slip, and it'll generate an earthquake. So the largest earthquakes on Earth and the deepest ones occur along these subduction zones. The Tohoku quake that occurred some years ago in Japan was a classic subduction zone earthquake. And a very similar quake occurred here in the Pacific Northwest in January of 1700. Native Americans were here at the time, not Europeans primarily, but the quake was recognized because it generated a huge tsunami that swept across the Pacific Ocean basin and struck Japan. Okay. The other thing, besides generating big earthquakes, is when that oceanic plate sinks under the leading edge of another plate, like the North American plate, it takes water down into the Earth with it. And adding water to the hot rock in the mantle causes that mantle rock to melt. And then those magmas, being less dense and buoyant, try to find their way to the surface. Now, most of them never make it to the surface. They get stuck somewhere in the overlying crust, and they cool and solidify. And then when we go out and look at them today, if they're exposed by erosion, we see plutons, like Castle Crag. Plutons are just big bodies of crystalline rock that form from magma that's solidified underground. Okay. Another thing, though, is that some of that magma does find its way to the surface, and it erupts to form a chain of volcanoes above the place where the plate is sinking. So Mount Shasta and the other high cascade volcanoes sit above the place where today the Gorda Wanda Fuca plate is sinking under the western edge of North America. And this same process has been going on here in the Pacific Northwest for hundreds of millions of years as plates have subducted along the western edge of the continent. Okay. So this is hard for me as a teacher because normally I'm thinking I'm in front of a classroom and people are going to raise their hands and ask questions. So I know that Renee and Kim are monitoring the questions that are coming in. But if something I say is not clear, just kind of make a note or put down a marker, and then we can come back and talk about it. So like I say, normally oceanic lithosphere subducts smoothly or relatively smoothly. But sometimes you'll have a part of the plate that is either thicker or less dense than usual. Okay, thicker, maybe you have an island built on it by a hotspot like Hawaii that makes the plate thick. Okay. Or maybe you have an oceanic subduction zone, like the one that built the Japanese ark, and there the rock is actually less dense than normal ocean lithosphere. So sometimes the plate can be thicker, sometimes it can be less dense, but the bottom line is normal ocean lithosphere sinks, and then this thickened part reaches the subduction zone and it jams up the subduction zone. It can't subduct, okay? So it gets stuck or sutured to the continent. We literally add a piece of new material to the edge of the continent. Okay, now, even though the subduction zone got jammed up, the stresses in the earth that were causing subduction, those didn't go away. And so what usually happens is the ocean lithosphere on the seaward side of that accreted block breaks and subduction begins again. And then here comes another oncoming block that can come in and be accreted. And so what happens is that continued convergence causes additional terrains to be added one after another as long as subduction is continuing. Okay? So you can stack up a whole series of terrains. Okay, so here's a geologic map of the Klamath. And probably the first thing that stands out to most folks is these curved colored belts of rock. Okay? Each of these curved colored belts is a terrain. Okay? So it's one of these, probably an offshore island chain, or, well, most of them were offshore island chains, volcanic arcs that were offshore. And as the intervening ocean floor subducted under the western edge of North America, those terrains were added one after another to the continent. The oldest ones are over here, the youngest ones are to the west. And then you'll notice cutting through these terrains are these red blobs. Okay, this is the Woolly Creek batholith, for example, the Iron Mountain batholith. Right over here, that's Castle Crags. Okay, and these are those plutons. So remember, once a terrain collides and gets added, subduction jumps west. Now ocean lithosphere is going down under that new terrain. Well, that subduction triggers melting in the mantle and magmas that rise up into the crust. And even though these red blobs were underground when they formed, uplift in the Klamath has exposed them so that we can see them at the surface today. Okay. And then the thing you might notice on this map, you see all these black lines with saw teeth on them, like this one right here. These are the terrain boundaries. These are actually faults. They're called thrust faults, and they separate the individual terrains from one another. And what they actually mark is where the old subduction zones used to be as each terrain came in and jammed it up and collided with it. So those faults mark the sutures between the successive terrains that comprise the Klamath Mountains. Okay, now I'm going to move on my screen. I'm going to move this so I can see it. Okay, so what I say here is the legend on this map over here shows the ages of the rocks in the Klamath. The oldest rocks are down here, and the youngest Klamath rocks are up here. These are younger rocks still, okay? And so it's oldest at the bottom and youngest at the top. And so if you notice, the purple rocks, those occur over in the eastern Klamath, just like you'd expect. And this sort of tan-colored rock, which is the youngest Klamath terrain, it's over here in the west, okay? So this kind of makes sense, right? Terrains are added to the edge of the continent one after another in succession. And so the structure of the Klamath Mountains, we see the oldest terrains over in the east, and then successively younger terrains that got smushed on outboard of them farther and farther west. Okay. Now, if you imagine a cross section of the Klamath, so imagine you could trench right across this line and then turn that piece of the earth up on end and look at it sideways, you'd see something like this. These are those thrust faults, right? So as each terrain comes in, it gets shoved under the older ones until it jams up, and then things break over here and the next terrain comes in after that. So we have the oldest terrains over here in the east, and then successively younger terrains shoved in under them and separated by these faults that mark where the old subduction zones were as terrain accretion occurred. This is an old classic cross-section drawn by Porter Irwin in a paper that he did on the Klamath years ago. If you study Klamath geology, Porter Irwin's name is going to come up a lot. He's a USGS geologist who's done a lot of the work on the Klamath. Okay, so we'd like to know a couple of things. First of all, how old are these individual terrains? Where did they come from? And when did they get added to North America? Geologists would like to ferret out the answers to all those questions. And so I have a little bit here to talk about that. So most of the Klamath terrains consist of either marine sedimentary rocks or volcanic rocks. Okay, well, that makes sense. We said that these were pieces of ocean lithosphere that were trying to subduct under North America and got smushed on instead. Some of the terrains include mantle rocks, like the Trinity terrain here in the far eastern Klamath, and some include plutons. But for the most part, we're talking marine sedimentary and volcanic rocks. Okay, so you think about sedimentary rocks, well, maybe we could use fossils to figure out what the age of the rocks is. And with marine sedimentary rocks, the problem is that during terrain accretion, these things are often heated and squeezed and faulted and sheared, and the old minerals that were in the rock break down and new ones sometimes grow at their expense. And so the result is the rocks don't preserve their fossils very well because they get recrystallized. But in a few favorable cases, they do preserve their fossils. And a really good example of that is the McLeod limestone, which is found down at Lake Shasta Caverns. And you can see these fossils here, these are horn corals. So they're not alive today, but in the Paleozoic era, these were huge solitary corals that built reefs around tropical islands. And so this limestone is in the Redding subterrane, part of the Eastern Klamath, and it tells us these rocks came from the tropics, okay? And what's really interesting about these horn corals is there were other horn corals alive in North America at this time, in the late Paleozoic, and they're nothing like the horn corals in the McLeod, which tells us the McLeod came from far to the west, okay? In fact, these horn corals bear more similarity to ones that were living in Asia at this time than they do to North America. So what this means is these corals built a reef around an island chain. That island chain was ferried across the Pacific on a subducting plate. And when it got to North America, that island chain, including the reef, got smushed onto North America. And so these fossils came from the tropics, where we're in the mid-latitudes today, and they came from actually closer to Asia than from North America. So some of these terrains are very, very far traveled. Okay, now the volcanic rocks, they're pretty interesting. If you drive along I-5, you'll see outcrops up between here and the Collier Rest Station that are pillow-like. Well, we can actually see rocks like this forming on the seafloor today. These are pillow lavas, and they're basalt lavas that were erupted from a ridge where the seafloor was growing, and then basically ferried to the western edge of North America by plate motion, and then the terrain that they were part of was accreted. And so in the Klamath Mountains, we see both seafloor basalts, and we also see lavas and pyroclastic or fragmental rocks from island arc volcanoes. So we know that some of the rocks that got added in the Klamath would have been chains of islands like the Japanese archipelago. Now, for those of you who are familiar with this, you say, hey, volcanic rocks, could we date those? Well, yes, maybe, but here's the problem. So the way this works is that some minerals in these rocks contain a radioactive parent element. So when the mineral crystallizes, it has only parent in it. And then over time, that parent decays to a stable daughter element. Okay? So if both elements stay put in the rock, and we know the rate at which parent decays into daughter, we can measure how much parent is there, we can measure how much daughter is there, and we can calculate the rock's ages. Okay? So this seems like it should work out great. Okay? But there's a problem. Terrain accretion is a really violent process, and it heats these rocks, and fluids alter the rocks, and you go from nice fresh lavas that look like this to really altered lavas that look like this under a microscope. So this is a fresh basalt seen under a microscope. You can see the various crystals. This you could probably date. But when you go and you sample it in the Klamath, you see how it's all turned green? It's all altered inside. And so the problem is that the daughter element is lost when that alteration occurs. And so a lot of the volcanic rocks in the Klamath, unfortunately, are too altered to be dated directly. Okay? So we use fossils where we can, and then there's some other ways we're going to get at dating. Okay. So remember we talked about those plutons, those bodies made of magma that rose from an underlying subduction zone, lodged in the crust, cooled and solidified. And if one of those comes up into a terrain, like right here, well, we know it must be younger than the rocks of that terrain because it cuts across those rocks. And then similarly, if a pluton cuts across the boundary between two terrains, we know it must have formed after those two terrains were already sutured together. Okay? So we can use the plutons as sort of pins that pin the terrains together, and that if we can date those plutons, then we can figure out when those terrains formed and when those terrain accretion events occurred. Well, the good news is a lot of the plutons, since they formed in place, aren't as altered as the volcanic rocks. They also have some minerals like zircon that are very resistant to losing daughter. And so we can often date the plutons. And a good example here, here are two terrains, okay, the Eastern Hay Fork and the North Fork terrain. And we like to know, when were they sutured together? Well, the English Peak Pluton cuts right across that suture. So if we date this, we find it's 162 million years old. So we know these two terrains had already collided and been sutured together prior to 162 million years when the Pluton formed. So by combining lots and lots and lots of measurements like this, geologists can put together the story of the formation of the Klamath. Okay, so I say using the ages of the Klamath terrains, and those are the collisions that suture together, geologists have put together roughly the last 400 to 500 million years of the range's history. And what we find is that most of the terrains that make up the Klamath, 7 of them, were accreted, were added to North America between about 400 million years ago and about 115 million years ago. Now, if you think back to what was happening on Earth at that time, the Atlantic Ocean began to open roughly 200 to 250 million years ago, okay? So the Atlantic didn't exist before that. And it actually split part of Pangaea and began to open. Well, that meant that North America had to move westward, right? As the Atlantic Ocean opened, the North American plate moved away from the Mid-Atlantic Ridge, it moved westward, and it essentially began overriding oceanic plates that lay under the Pacific Ocean basin. And so it's at about that time that subduction began in earnest along the western edge of North America. And then remember, it's that subduction that's tied to the accretion of these terrains. So here's a paleogeographic map showing what Western North America was like about 200 million years ago. This line here is the subduction zone, and you can see some terrains, some bits of terrain coming in. And of course, these are going to jam in here, and it's terrains up at about this latitude that would be forming the Klamath Mountains. Okay. Now, one other thing. So, under fortunate circumstances, we can actually use the magnetism preserved in the rocks, in certain volcanic rocks, to tell something about how much terrain has traveled to get to us, and if it's turned around at all. Okay. So basically, you guys probably know, because of Earth's rotation, there's circulation in the outer core of the Earth, and that generates the planet's magnetic field. And so close to, but not right on, usually, the North geographic pole and the South geographic pole are the North and South magnetic poles. And because the magnetic field is generated by the planet's rotation, those magnetic poles tend to stay fairly close to the geographic poles, okay? And when a rock, like a basalt, solidifies, initially it's molten and tiny crystals of the mineral magnetite grow in the rock. And when that rock cools to about 570 degrees centigrade, those little magnetite crystals lock in a record of the direction of the magnetic field at that time, okay? And as long as the rock isn't too badly altered or reheated above 570 degrees, that record of the orientation of the magnetic field will be preserved. So geologists can go out with a core drill, they can drill out cores, and then they can actually measure the ancient magnetic field direction preserved in the rock. Now, of course, in the Klamath, you've got issues with alteration and deformation, and so there's lots of complexities that need to be taken into account. But one thing you can get from this is approximately the latitude at which the rock formed. And that's because near the poles, the magnetic field lines dive steeply into the Earth. You can measure that in the rock. Near the magnetic equator, the magnetic force lines are roughly parallel to the Earth's surface. So you can actually measure what's called the magnetic inclination preserved in a rock and get some idea of the latitude it came from. You can also get an idea of what the ancient pole direction was. And one of the interesting things about this is that we can see that some of the oldest terrains in the Klamath have undergone tremendous rotation since they were accreted. So they were accreted to North America, and then North America has changed orientation and turned those old terrains around. The oldest terrains, some of the Eastern Klamath terrains, have rotated 110 degrees since they were accreted a little bit after 400 million years ago. Okay, so what's happened since terrain accretion? Well, terrain accretion ended about 115 million years ago, but subduction didn't. It continued. And today, the little plates that we have subducting along the western edge of North America, they're the remnants of a larger plate called the Farallon plate. But as that plate subducts, material is scraped off its surface and piled up against the western edge of North America in what's called an accretionary wedge. And that's the Franciscan complex that you saw on the map. Now it's what the French would call a mélange. It's a mixture, so it's seafloor sediment and bits of basalt from the seafloor crust and all sorts of other rocks mixed in there. But subduction is occurring and that accretionary wedge is still growing. Now, between about 115 million years ago and roughly 5 million years ago, the western edge of North America, the part that is the Klamath, was relatively quiet tectonically. Certainly not completely so, but relatively quiet. And what that allowed was for the Klamath River and its tributaries to erode those accreted terrains down to a flat, relatively low elevation surface. So when those terrains came in, those were violent collisions, and you certainly would have had an upland, right? But then over the last 100 or so million years, erosion worked its magic, and the Klamath and its tributaries cut that down and had produced an erosion surface that was relatively flat. In fact, the western edge of it had actually subsided to the point where it was below sea level, and marine sediments were deposited on the western edge of that old erosion surface. They call that the Klamath Peneplain. And if you stand in Roseburg, Oregon, and look south towards the Klamath, you can see that the top of the Klamath defines this fairly straight, flat surface. That's the old erosion surface that developed during that period of relative tectonic quiescence. Okay, but nothing ever lasts. So during the past 5 million years or so, maybe 5 to 10 million years, we've had renewed uplift in the Klamath, okay? And it raised the mountains to their present heights. Now, part of what that did was lowered the base level of the Klamath River and its tributaries, so they've cut down into the Klamath. And the Klamath River is really interesting in that it goes from east to west across the mountains, although as you saw in those earlier maps, the geologic structure of the Klamath is primarily north-south. And so the fact that the river has maintained that east-west course, it suggests that it established that course when the Klamaths were a relatively low area, and then it's been able to downcut and keep up with the uplift during these past 5 million years. So today we've got these mountains that have been incised by the Klamath River and its tributaries due to relatively recent uplift. Okay, then beginning about 2 million years ago, you know that Earth entered an ice age, the Pleistocene, okay? And so an ice age doesn't mean there's big glaciers there all the time. What it means is glaciers form and advance, and then they retreat, and then they form and advance, and then they retreat. So you have a series of episodic glacial advances. Well, those glacial advances have sculpted the highest parts of the Klamath into a rugged alpine landscape. So you have horns, and you have cirques, and you have all the traditional features in the geography that are created by glacial erosion. Okay, now the last major glacial advance peaked around 22,000 years ago. It ended around 10,700 years ago, and we've been in a relatively warm period since then. And so, although a few small glaciers or perennial ice fields hang on today in the Klamath, erosion is dominated by landslides and streams. So now, a couple quick words about mineral resources, since probably what got the Europeans really interested in the Klamath initially was gold. So when you have one of those bodies of magma in the upper crust cooling, one of those things that's going to become a pluton, groundwater gets down to it and gets heated, and also the pluton releases some water that was originally dissolved in the melt. And so you get this hot water circulation above a cooling pluton. And that hot water will actually dissolve and carry small amounts of metals and large amounts of silica from the rock around the pluton. So that fluid goes out and it scavenges those metals and that quartz, that silica, and then that hot water ascends through fractures above the pluton. Well, as the water's flowing towards the surface, it's cooling, and as it cools, those dissolved metals and silica become less soluble, and so they get deposited out in those fractures. And those are the veins that lode gold miners were always interested in, okay? So it's a little hard to see. This is a piece from the Scott Valley. There would have been rock wall here, fluid flowing up through this crack, and you can see the quartz crystals that grew from this side and grew from this side, and almost, but not quite, closed off the center of this vein. This was actually collected over by an old stamp mill that used to be by Munkinsville. And so miners were mining the quartz out of these veins and then crushing it. And what they were interested in was the gold that was in with the quartz. Okay. Now, nature does some of this work as well. So these veins will erode where they're exposed at the surface. Gold doesn't weather significantly, so it's released when the vein breaks down. And then that gold is in the soil, it's washed into streams, and then it's moved downstream during floods, and it's locally concentrated into placer deposits because it's so dense. It's over 19 times as dense as water. And so it ends up at the bottoms of the channels. And so as anybody who spent time in the Scott Valley or along the Klamath knows, in the past, beginning in the 1800s and continuing, I think, almost until 1950, dredges were run along the rivers, and they would dredge up all of the river gravel, run it through a sluice essentially, and get out the gold and leave behind these huge volumes of tailings that we see over by Callahan, for example. Okay. During the Second World War, a mineral that everybody was interested in was chromite, because chrome was needed to harden steel during the war, and our supply from South Africa was cut off. And it turns out in the crust, in the ocean crust, basalt magma, as it cools, sometimes crystals of chromite will grow in the magma. And being denser than the magma, they settle to the bottom, they make layers of chromite, and normally that chromite would be in the ocean mantle, and it would simply be subducted back into the earth. But because of terrain accretion, some pieces of mantle rock were actually pushed up onto the edge and cemented on or accreted onto the edge of North America. And so we have chrome deposits in the Klamath Mountains. There's some up by the pass between Wairika and Fort Jones. Just, I can't think of the name, Forest Mountain Summit. There's some chromite mines up there. There's a chromite mine that used to be active during the war down by Castle Crags. Those mines all basically shut down after World War II because it was much less expensive to get chrome from overseas sources than it was to mine it locally. Another mineral deposit that's kind of interesting, and some of you may have heard about, the alteration of mantle rock to serpentinite produces very alkaline waters. And those alkaline waters can pick up small amounts of mercury from the crust. And then it's just like with the quartz veins, that water bearing the mercury flows through fractures. And as it cools, it deposits the mercury, and mercury shows up as this beautiful red mineral. This is cinnabar, the mercury sulfide, and it's typically in veins with calcite. And so there are a number of mercury mines in the Klamath Mountains. Perhaps the most famous is the Altoona mine, which operated from, I believe, the late 1800s, and the property was still intact in the mid 1900s. I actually visited it some years ago and collected these samples. But the problem here was there was a tremendous amount of tailings with mercury in it. And when it rained, mercury was leaching out of those tailings into a tributary of the Trinity River, and it was showing up in the fish down in Trinity Lake. And so people backtracked the mercury, figured that it was coming from the old Altoona mine. And so some years ago, a big hole was dug. It was lined with geotextile, and all these tailings were put into it. Clay cap was on top. So you can't really go and see where the mine was anymore, but it's no longer leaching mercury into the Trinity. Okay, so geologic hazards in the Klamath Mountains. So, today, due to uplift and then incision by the Klamath and its tributaries and by glaciers, we have really steep topography. But we also have rocks that are fractured and altered during accretion, so they're not very strong. So the combination of steep slopes and fractured, broken rocks means that mass movements, rock slides, slumps, debris flows, that's a very serious hazard. And then of course, it can be made worse if old roads aren't decommissioned, that roadbed becomes a potential place for failure. Or if we have a forest fire that removes large amounts of timber, the roots would help anchor the soil, and without that, then the rains are going to cause more severe mass movements, landslides. Flooding is also a threat. People live in fairly deep, narrow canyons on or near the floodplain, and so it's just a matter of, time. Over time, streams tend to have high discharges, and so flooding remains a serious threat in the Klamath. And then, like I mentioned earlier, because we have such diverse rocks, I mean, we've literally ferried these rocks in from across the Pacific and added them to North America. We also have microclimates in the Klamath, which means the rock weathering proceeds at different rates and to different degrees. in different places, we end up with a very diverse array of soils in the Klamath. And here's a part of the soil map, the NRCS Web Soil Survey map. Here's the Callahan is down about right here. This is the Scott Valley, and then the Klamath Mountains just east of that. And in this little polygon that I outlined, there's 241 separate soil types. So tremendously diverse soils because of the diverse rock types and because of the diverse microclimates. And then of course, in turn, those soils support a tremendous diversity of different types of plants, including a number of the endemic species. Okay, so this has been my 60,000-foot overview of the geology of the Klamath Mountains. And you guys will probably want to read more. And so Porter Irwin and his colleagues from the USGS have published a number of classic papers on the geology of the range. Some years ago, the Geological Society of America also published a special paper with original articles on the geology of the range. And then more recently, Mark Bailey has written a chapter, an overview chapter on the geology of the Klamath Mountains as part of a forthcoming book on Klamath natural history from Backcountry Press. And so what I've done is I put together a web page. You can see it here, and here's the address, and put links to all those USGS publications and to the GSA special paper, although you would have to buy it for the princely sum of $10 from GSA. But all the USGS papers are free, and there's a wealth of great resources out there on the geology of the Klamath Mountains. Okay, so my last comment. What I said is after more than 150 years of exploration and study, Western geologists have just only begun to understand the processes that have built the Klamaths. The Klamaths were just a nightmare for people doing geologic work, because every time you cross a fault into a different terrain, the rocks would tell a different story. They've come from somewhere else, they're of a different age, they represent a different geologic setting. And so accreted terrains, really it's only been since the 60s that we've understood how this process occurs. The native peoples in the mountains know the mountains intimately, but they often don't frame their knowledge in a Western context. So a challenge, I think, in the coming years will be to integrate these complementary perspectives, because we expect to see changes in the Klamath due to population growth and due to warming climate. And my dog has a question. She asks if we can go play Frisbee now. But first, we have other questions. So thank you very much.
All right, thanks so much, Bill. And I love that the upcoming book that you referenced on the history of the Klamath Mountains, that is a book from Backcountry Press, which is of course Michael Kaufman, our webinar from last month. So it's great that all of these pieces are tying together. So we do have some questions for you, and I'm just going to start from the beginning. Early on in your presentation, Josh Larson asked, are there any new forming volcanoes in the Klamath region?
No. The volcanic arc today lies to the east of the Klamath. So the Gorda and Juan de Fuca plates are subducting under Western North America at a fairly shallow angle, less than 15 degrees. And they have to get down to a depth of about 100 kilometers before enough water is released and enough melting occurs that it can make magmas. And so if you think about the subduction zone lies offshore off the Northern California and Oregon coast, you have to come about 150, 200 kilometers eastward till you get to the point where the plate has reached a depth of 100 kilometers and significant melting is occurring. And so today, the active volcanic arc is here in the Cascades, and it lies to the east of what we think of as the Klamath. But interestingly enough, there are places like Yellow Butte, which is just north of Mount Shasta, where a fault has actually brought up some of the deep basement rock, and it's Klamath rock. So the eastern Klamath terrain continues under the modern Cascades for some distance farther east. We just don't know how far. and there's actually some little volcanoes out just east of Mount Shasta that the lavas are really rich in magnesium. And what people think is that maybe the lava is coming up, it's sort of normal basalt, but it's coming up through the old serpentine of the eastern Klamath terrain, and it's digesting that and incorporating the magnesium from that. So the volcanoes associated with modern subduction lie to the east of what we think of as the Klamath Mountains, but they may still be being built on old Klamath basement in the subsurface.
All right, thanks. So next question from Dan Scullion. Can you speak to the question of whether the Klamath traced their origin to the present desert Southwest, rotated and moved into place along strike-slipped faults?
Oh boy, Baja, BC. So I didn't really touch on that in this presentation, but what Dan's mentioning is there are several hypotheses that along the western edge of North America, we had quite a large shear zone in the past. And there are some, what they call pendants down in the Sierra Nevada, like the Snow Lake pendant. And it's been suggested that rocks were translated, that is slid northward from the latitude of Baja California up to the latitude of British Columbia, and that there's the Sonoma megashear, I think it's called. So there are hypothetical faults that have been invoked to suggest that these terrains have been slid along the western edge of North America long distances. And I'm not an expert on those hypotheses, and so I don't want to go and say something that I don't know for sure. What I will say is that the rocks of the Klamath, there's an interval south of us, south of about Lassen Peak, where those rocks are covered by things like the Tuscan Formation, but then the rocks of the Klamath reemerge in the northwestern Sierra Nevada, the gold rush country, basically. And you can match up pretty much one for one the terrains of the Klamath Mountains with the rocks of the northwestern Sierra. So the accreted terrains weren't just accreted here in the Klamath. They were accreted along a longer segment of the western margin of North America.
Okay, all right, thanks. And Kirk Emson from Facebook asked, what led to the renewed recent uplift in the last 5 million years?
That's a good question. I'm not really certain. It partly, when you have subduction like this, you continue to basically, I'm going to do it with my hands. It's kind of like sweeping stuff under a rug, right? You push stuff under the margin of the continent, and you uplift those ranges. So it may be a change in the rate, or the angle of subduction has simply led to an increase in the uplift. The other thing is that there's some evidence of earlier uplift. There's a huge detachment fault in the Klamaths. And detachment faults occur when you uplift the crystalline basement and the rocks on top sort of slide off. So the problem is that past episodes of uplift, to some extent, they've sort of removed evidence of themselves, in a sense, that you've eroded that material away and lost it. So probably the story is much more complicated than this sort of simple narrative, but I don't think it's really, really well understood.
Okay, all right. I've got to keep track. We've got more questions coming in. Let's see. Anna Roz asks, are there any caves with significantly exposed deposits in the Klamath Mountains?
There are. I have seen a few. So, and I would be hard pressed to tell you where it was, but the McLeod limestone, of course, has the commercially developed Lake Shasta caverns in it, but it also has a number of other caves, Samwell Cave and so on. And then the Marble Mountains, it's another limestone, presumably a reef or a bioherm, and it has caves. The one of those that I visited, you can only go in a little ways and then the cave is flooded. But there's an inventory, I believe, done by the Forest Service, and then certainly the National Speleological Society has kept track of this. But there are plenty of caves in the limestones of the Klamath Mountains.
All right. Sandy Graham asks, is it likely that plutons are underground as well?
Oh, yes. Yeah. We only see, the ones that the current erosion level has penetrated down to, but there's almost certainly others that are not yet revealed.
All right. I know I've sort of lost track of it, but I know that someone had posted a question earlier asking if you were going to speak about serpentine rocks.
Sure. So serpentine is basically, if you go underneath the crust, the rock of the upper mantle is called peridotite, and it's basically a 1 or 2 mineral rock. It's the mineral olivine and then a pyroxene, 1 or 2 pyroxene minerals, and it's this beautiful green crystalline silicate rock. During rifting at a mid-ocean ridge, huge fractures develop around the rift, and water can get down deeply into the crust and the upper mantle. And there's magma right underneath a mid-ocean ridge, and so the hot magma circulates seawater through the crust. It deeply alters the oceanic crust, and then it can also significantly alter the upper mantle. And so what you do is you effectively add water to these dry magnesium silicates. And the result is serpentinite, which is a rock made of serpentine. They're water-bearing magnesium silicates. And so it's this green or black rock. It's often fairly soft. It often shears, so you'll get lens-like phacoids, these lens-shaped fractures in it. And then it can be remobilized, and in fractures, the fibrous form will grow, so you'll get asbestos, basically. So there's lots of it here in the Eastern Klamath. So the Trinity subterrane is basically, it's the mantle roots of an old 400 million year old Ordovician arc. So there's lots of serpentine in the Trinities, in the very Eastern Klamath. And then there are several other serpentinite bodies throughout the range. There's a serpentinite that's part of the Josephine ophiolite farther west. So normally that material would be subducted. You wouldn't see it again. But during terrain accretion, sometimes an ocean basin gets pinched closed, and some of that serpentine or altered peridotite gets pushed up onto the crust. And that's happened in quite a number of places in the Klamath.
All right, so a question from Forrest Lamb on Facebook. I've always wondered about Mount Eddy. It looks like it could have been another large volcanic mountain at some time. Was it?
No. Mount Eddy is underlain by the serpentine in the Eastern Klamath, and that nice pointed shape, I mean, it's not a true glacial horn, but the Trinity, that part of the range, there are glacial cirques up there, and it was carved by glaciation, but it's an outcrop. If you go up and climb Mount Eddy, you're standing on serpentine on top. It's part of the Trinity subterrane.
All right.
So it's old ocean mantle rock, basically.
All right, and here's a question from John. John, I'm not going to try to pronounce your last name because I know I'm not going to get it right, but he asks, can you talk about the very extensive outcrops of ultramafic rocks northwest of Weed? There are also a lot of veins in these rocks. Oh, and he corrected, west of Weed near Mount Eddy.
Same thing. That's the Trinity complex. So that's the Eastern Klamath terrain has 3 subterranes, and the middle one, which was the deepest and which is separated from the other 2 by that detachment that I mentioned, that has been lifted up. And what you're looking at is old oceanic mantle cut by big gabbro pluton or hornblende gabbro plutons. And so all of that serpentine, you know, that if you go up over the IP road, up above Stewart Springs, for example, the outcrops all along that road, that's the serpentine of the Trinity subterrane.
All right.
And it's a very hard rock to date directly, but the gabbros that cut it do have small amounts of zircon, and they have zircon ages of about 410 to 430 million years. So it's thought to be the upper mantle of a suprasubduction zone, of the mantle underneath an old Ordovician subduction zone. There probably would have been an arc sitting on top of it originally, but most of that volcanic cover has been lost.
All right. And from Arthur Rogers, would different accreted terrains reveal differences in deep crustal structure and lithology?
Deep. Most of the terrains in the Klamath that I'm familiar with don't represent really deep rock. They represent basically island arcs, mostly island arcs, built on old oceanic lithosphere. Think Japan, for example. There are terrains in other areas where basically you've broken part of a continent and brought the deep continental crust up into an accretion zone, and there you could see very deep rocks. But to my knowledge, in the Klamath, we don't see rocks from great depth. And the prevailing grade of metamorphism in the Klamath is, you know, green schist facies or amphibolite facies metamorphism. So we're not looking at really deep crustal levels, at least today.
All right. We've got a fun question for you. If you only had one day to be in the Klamath Mountains, what's the #1 must-see geologic feature?
Gosh. Well, let me answer it this way. I would take a drive from Gazelle out over the Gazelle Callahan summit down into the Scott Valley at Callahan. Then I'd drive north along Highway 3 and then come back over Forest Mountain Summit to Wairika. And you'd get to see the Gazelle Formation rocks. You'd get to see, let's see, would you see? I think you'd see some of the Trinity rocks up near the summit. You would see the Scott Valley, and you'd see the dredge spoils from the dredging in the Scott Valley. Then you'd go back up over Forest Mountain Summit, which takes you through a big serpentinite block in the Wairika subterrane. So you'd get to see a lot. Another fun trip would be to drive just as far as you could down the Klamath River along Highway 96, say start at I-5 and drive south. And you do go through several terrains there, although the boundary faults between the terrains are fairly subtle, and you almost have to have a road log and know where to stop to kind of know what you're looking at. But I did a field trip some years ago with a group, and we went down as far as the Condrey Mountain schist, which is a really interesting rock. So I would say trips either along Highway 96, west of I-5, or a trip going up over the Gazelle Callahan Road, north through the Scott Valley, and then up over the Forest Mountain Summit Road. Those would be really nice one-day trips through the Eastern Klamath, and you'd get to see quite a wide range of rocks.
Nice. All right. I've been doing that drive a lot the last couple of months. Let me see what else we have. Please comment on the relationship between the Klamath and the Northern Sierra Nevada. Are they essentially contiguous but bisected or overlain by cascade activity?
Yes. Yeah. So there's some question about, you know, there's a jog. So the strike of the units in the Northwestern Sierra and the strike of the units in the Klamath isn't quite the same. And some people want to put a fault under there or a fold. But as we mentioned earlier, the problem is that those rocks are hidden primarily by the Tuscan Formation. So rocks that erupted from the area of the Lassen Volcanic Center a few million years ago. It was not from Lassen itself, but from other cones in that area. And so, you know, it's one of those great problems in geology where you can see the rocks on either side, but you don't know what lies in between. So the nature of the structure is uncertain. But like I said, there's a terrific map, and I probably should put the link to it on that webpage that actually correlates the terrains of the Klamath with their counterparts in the Northern Sierra. And so, yeah, terrain accretion certainly went at least as far south as the Gold Rush country. In fact, my understanding is that's why when prospectors came through this area, why they immediately started looking for gold was they recognized the basic similarity between the rocks in the Gold Rush country where they had been and the rocks that they saw in the Klamath and the Wairika area.
All right. Let's see, I'm just taking a look to see if we've got, there are a couple of questions where folks are just asking about rock types and if they would be found in the Klamath. And so the questions are about blue schist and greywacke.
Okay, so greywacke, in the Klamath, the accreted terrains are overlain by a unit called the Hornbrook Formation. It's a Cretaceous marine unit, and it was deposited. There's a profound unconformity. It's well exposed along I-5, and where the basal part of the Hornbrook Formation sits on top of these pillow lavas of one of the Klamath terrains. And that's a gorgeous greywacke. That's the Hornbrook Formation. You see it if you go up to the Hornbrook-Henley exit on I-5 and look at the rocks along the interstate there, or just south of the Hornbrook-Henley exit. And it's a beautiful greywacke, very immature. Greywacke is an immature sandstone. And in places it's full of marine fossils and cobbles, and it's just terrific. Within the Klamaths themselves, I'm sure there are greywackes. There are probably meta-greywackes, though. There's always some degree of alteration. And then blue schist, it's not common in the Klamath. But there are certainly scattered blocks of it. And by far the most famous one, if you drive up Highway 3 west out of Wairika and you're on your way up to Forest Mountain Summit, so you're still on the eastern side of the summit, along the road there's a big boulder, and you have to be careful. It's easiest to get to it if you're coming east, but you can pull off. It's on the south side of the road, and it was called Robbers Rock. And apparently when that was a stage road, the bandits would hide behind the rock and rob the stage. And Robbers Rock is a blue schist block. So there are blue schist blocks tectonically interleaved with the serpentinite up near Forest Mountain Summit in the northern part of the Wairika subterrane. And if you look at geologic maps of the Klamath, there are a number of blue schist localities. They're denoted by these diamond-shaped symbols on the maps. But the problem with the Klamath is that a lot of the land is in private ownership, or you have to cross private land to get into places. So the only blue schist block that I can think of that I could point people to and that nobody would mind if you stopped and took a look at it is probably Robbers Rock up along Highway 3, just west of Forest Mountain Summit.
All right. Well, Bill, I want to thank you. There are still some questions hanging out, and we may forward those to you in email.
Okay.
But I want to say thank you to everyone who's out there, and thank you so much to Bill for sharing your knowledge and your enthusiasm for this area. And I love that you can just suggest roadside stops for folks. So thanks everyone for joining us tonight. I know there was interest in the link that Bill shared, a few slides from the end of his presentation. We'll pick that link up and we'll send it out with the email for all of you folks who are watching the webinar through Zoom, and then we'll also post it to Facebook so folks can find it there and follow up on some of those resources. So thank you to everyone. And with that, we will say good night. Have a great evening.
Thank you, everybody. Bye, Renee.
Bye, Bill.